this is Willem for Solar Intelligence. Today discussing how to size and better understand your solar system. This is the next video in our series of the how-to series of videos where we're on a mission to get to a complete understanding of putting together a solar system and understanding the different subcomponents. In the previous video, we discussed the three primary types of solar systems. Today, we're going to expand a little bit more, and we're going to discuss the details of the individual subsystems and the impact of their sizing on the total solution. Okay, a quick recap then of on the previous video. Previously, we mentioned hybrid systems or hybrid inverters. And remember, a hybrid system is a system that has both storage and generation. Storage in the battery and then generation from the solar panels. Right, so leading on from the previous video, we first need to determine what we are actually looking for. What is the journey and what system are we looking for? So I'm going to make a few assumptions. I'm going to assume that we are putting together a hybrid system. In other words, from the previous video, remember, a hybrid system is a system that has both storage, which is in the battery, and energy in the generation, which is the solar panels. So I'm assuming that you are looking for a system that has both those, and we'll talk about the subsystems too, and you've seen that already in the previous video as well. So moving on from there, that we are looking for a hybrid system. So we need to specify what this hybrid system needs to look like, what the size needs to be, so that we can get onto building and buying our own solar system. And you'll see in the subsequent video that we'll be making, we'll also be talking about the pricing and working out the price and the costing aspects of your solar system. But for today, we're just going to talk about the subsystems of a solar system and how they all link together. All right, so starting off, it's a hybrid solution. So we are on a journey to construct a hybrid solution, either with a hybrid inverter or a constructed hybrid system. And the detail of that is not currently important. The three subsystems. We know that there's the battery subsystem, which is the storage. There's the inverter subsystem, which is obviously converting the DC from the panels or from the battery to alternating current. DC meaning direct current. To make it alternating current, to be able to use that in the house. And then we've got the solar panels. We call that the PV generator. Remember PV, the word PV stands for photovoltaics. It's a bit of slang, but please excuse me for using PV. Whenever I mention PV, I mention the collection of solar panels on the roof. So the PV generator is basically the collection of solar panels on the roof that generates and harvests the energy from the sun, that we can make that available in the house. I'm going to explain a solar system's functionality with a simple analogy. The analogy that I draw is between a car or a bakkie, let's call it a little truck that needs to go up the hill, that's got a load on the back of the truck needs to go up the hill. I'm going to make the analogy of that to your solar system. All right, so for this little truck to be able to go up the hill, it needs an engine. That engine needs to be big enough to be able to pull the load to get up the hill. The analogy is with your inverter system, the inverter needs to be big enough to pull the load, so to say, pull the load, to carry all the loads that are switched on in your distribution board. That could be the lights, the TV, the fridge, the kettle, whatever is on. So the more loads you have on in the house, the bigger the inverter needs to be. The same with a little truck. The bigger the load on the back of the truck, the bigger the engine has to be to get up the hill. But the truck cannot go up the hill if there's no fuel in the fuel tank. So there must be energy available. The analogy to the solar system, there must be energy available, either stored energy in the battery or energy from the panels. So let's just focus on the battery for now. So the bigger the battery, the bigger the fuel tank. So whenever you think of a battery for a solar system, just think of a fuel tank for your vehicle. The bigger the fuel tank, well, the further you can drive. The bigger the battery, well, the longer your system will be able to run without running out of energy. In other words, the autonomy, the period during which the system will be able to run on the energy stored in the battery. If you are adding energy to the battery all the time from the solar panels, well, then you can go further on. The analogy to the car is, while you are driving, you are refueling the car. The same analogy would be, it's not that it's practical and real, but that's in essence what it boils down to. All right. And then how do the panels fit into this whole picture of the analogy with the vehicle? Well, how do you refuel your vehicle? How do you fill the tank? Well, you go to the fuel station and you put fuel in the tank. With the solar system, you can refuel the battery, or you can recharge the battery one of two ways. Either the Eskom power can charge the battery, that is now the fuel supply, or you can have another fuel supply coming to charge up the battery, and that is then the solar panels that are also adding energy to fill up the battery again, so that you can carry on further. Does that make sense? You're welcome to use that analogy. All right. So let's talk about the inverter subsystem. So what does the inverter subsystem do? Well, the inverter is the engine. The inverter does the work the same way that the engine does the work. The bigger the load, the bigger the engine. Either the bigger the load in the distribution board, the more items you switch on. So if you say, I would like to add my oven, I would like to add my geyser, those are all heavy loads, and we'll talk in a subsequent video about the loads as well. Those are heavy loads, which means that you'll have to have a bigger inverter on. So the more items you have on at the same time, the bigger the inverter has to be to power all those items at the same time. So concurrent use and concurrent switch on, that means the inverter has to be bigger and bigger. All right. So the inverter does the work. So let's talk about the sizing. This video is about sizing your system. So let's say, what happens if the inverter is too big? Well, not much. The inverter is too big. Well, then you've spent money on an inverter that can offer more power or carry a bigger load, but you're never going to use that bigger load. So you've just actually wasted money. So not smart. If you're budget conscious, like I am, then you want to make sure that your inverter is just the right size. Okay, too big is not really a big issue. It's just a financial impact. What if the inverter is too small? Well, if the inverter is too small and you switch on the kettle or you switch on the microwave or whatever it is, and if that item that comes on takes the inverter beyond its capacity, so let's say it's a 3 kilowatt inverter and the load that you're expecting to come from this inverter is 5 kilowatts, well, the inverter will shout, say, I can't do that, and the inverter will shut down. It's damaging, it's dangerous to do that with inverter all the time. If you keep on overloading the inverter like that, the inverter will probably fail in due course. So to get out of that condition, you'll have to go walk in the dark to wherever the inverter is and reset and restart the inverter to get the inverter back up again. So if the inverter is too small, that's a big frustration, and most likely in the long run you'll be damaging and probably destroying that inverter, and you'll have to have it replaced. And most warranties exclude overloading. So make sure that you choose your inverter well. All right. Let's get to the battery. What is the battery's function? Well, we said for the little truck, the analogy again of the vehicle going up the hill, if there's no fuel in the fuel tank, well, it doesn't help if you've got a beautiful V8 engine that's got so much power, but if there's no fuel, if there's no energy to power that engine, well, then you're not going to go anywhere. The same with your solar system. If there's no energy in the battery, then the inverter can't do the work. So the battery is the stored energy or the potential to do work. It enables the work to be done. So the bigger the battery, the longer the system will be able to run. Obviously, the same with analogy with the vehicle. The harder your foot is on the pedal, the quicker you are consuming your fuel. The same with your solar system. The more items that are on in the DB, well, the quicker you are going to exhaust, or you can deplete the energy from the battery. Okay, so let's talk about battery capacity. So what if the battery is too big? If the battery is too big, again, no big issue. It'll take longer to recharge it. So if you recharge it with your grid utility, with Eskom power, well, it'll take a little bit longer, depending on the capacity, the charging capacity of your inverter. It'll take a little bit longer to recharge the battery, but you've got then a bigger fuel tank. So same with the analogy with the vehicle. Bigger fuel tank, well, it's not an issue. You've got to put more fuel in. It's going to cost a little more. But once the tank is full, you can run longer. But it's quite expensive. Batteries are quite expensive. So to overcapitalize or to spend too much money on a battery that is bigger than what you require is actually not that smart. What if the battery is too small? Well, here's an issue. So if you were watching the rugby the other day and the Springboks are still 5 points behind and there's only 5 minutes left and you have to watch the end of the game, imagine at that point your battery runs out of energy and your TV shuts down. I'm sure you'll never forgive yourself for that. So if you want to see what happens in the last 2 minutes of the game, well, the battery's going to be big enough. So if the battery is big enough, you'll get enough endurance or autonomy out of the battery to get to however long you want it to last. So I often get the question, but how long will this battery last? Well, what is on at the same time? If you switch on your heater or your stove plate or the oven or whatever it is, that's a big drain, it's a heavy load. It will deplete the battery very quickly. But if you only have a few lights on, a light TV, fridge, well, then a smallish battery can take you easily through 4 or 5 or even more hours, depending on what's on it. So the bigger the load, the quicker you are depleting the battery. Make sense? All right, let's talk about the PV subsystem, the PV generator. Remember PV? Photovoltaic, solar panels. The solar panels have 2 functions. The solar panels must recharge the battery. As we said, we need to replenish that energy so that tonight when the sun sets, we've got some energy in the battery for when Eskom strikes, as it does. But the solar panels must also keep the house going during the day so that we can render some savings or get some benefit from the solar panels. So the panels must do two things. It must keep the load going during the daytime. So whatever is happening in daytime, whether the washing machine is on and maybe a vacuum cleaner or an iron or whatever. So we always design our systems so that we have enough solar panels to keep the house going during the day and to replenish the energy in the battery. So that tonight when the sun sets on an average sunny day, that we have the batteries full and we can go through the night. Okay. So what is the challenge? If I've got too few solar panels, well, we call it energy starvation. There's not enough energy coming from the sun to keep the house going and charge the battery. So typically these systems are programmed, we can program it with, depending on what you're installing, that the priority is either to charge the battery or to keep the house going. So mostly I would suggest keep the house going because that's real savings. Every watt that you harvest from the sun and use directly from the sun is a watt that you don't have to buy from your supplier. So if your PV generator, the solar panels are too few, or you haven't got enough, your PV generator is not big enough, then there's not enough energy from the sun to keep the house going and to recharge the battery. So when the sun sets, the battery might not be full, and then half an hour or a few hours into the night, the inverter will shut down because the battery is empty. That's obviously if there's no ESCOM power. All right, so that is if the PV generator is too small. If the PV generator is too big, well, that's a big thing. I'm going to spend a bit of time later to talk about the PV generator and the ratio between your load consumption, the battery size, and then the PV generator. And there's a big important relationship that many installers miss that you need to understand. But in essence, if you have too much PV on the roof, too many solar panels on the roof, then you harvest more energy than what the house is using and what you needed to recharge the battery. So if the battery is full and the house is not using the energy, where is that extra energy going? If you're in a fortunate situation where you can sell energy back to your supplier, whoever it could be, maybe an estate that you're living in or the township or the area that you're living in, you're allowed to feed back energy to the grid, well then you can sell that energy and then back to your supplier. But here in Gauteng, there are not too many municipalities that actually allow that. And by the way, that's another video that we'll be discussing as well, feeding energy back into the grid. All right, so important, I'll get to it now, to talk about what if you've got too much solar power. All right, let us then talk about the relationship between these three, the PV generator, the storage in the battery, and then the inverter capacity. And for that, I'm going to go to a PowerPoint presentation. As mentioned, I'm going to be using a PowerPoint presentation just to guide us through a little bit of detail about the typical load profile and the impact then that it has on the three primary subsystems. So again, just to recap, three primary subsystems, the PV generator, the battery, and the inverter. All right, so let's go into it. So first off, we start with the typical residential load profile. So what I mean with that, the typical household, how does the typical household use electricity? So in this graph, we can see on the left-hand axis, that is power. You'll see that is in watts, or 6 kilowatts. The maximum is 6 kilowatts. And on the horizontal scale, that is time of the day. So there's a 24-hour period from midnight to midnight, showing in red how much power this house is using. So as you can see, here around about 3:40 in the morning, there's a big load coming on around about 4 kilowatts. That's typically a geyser. That's probably the geyser coming on, obviously heating the water for the people when they wake up in the morning that they've got hot water. And here at 5:30, you can see there's quite a bit behind the label there, quite a bit of energy consumption, more than the geyser, the geyser's power. That's obviously the kettle and the toaster and whatever else the people use to prepare their breakfast. And you can see they depart for work probably around about 7-ish. And then there's not much happening. Then early morning, here around about 8-ish, there's a load of some 2 kilowatts. It's probably an iron or a washing machine, vacuum cleaner, and a little bit of consumption during the day. Only then again, late afternoon, here from about 3 o'clock, you can see there's quite a bit of power being consumed again. There's probably again the geyser coming on, and some more, maybe a plate, oven, or something that comes on for preparing dinner then for the residents in the house. And then for the rest of the night, as you can see, not much we call that base load. So the base load here, that's basically how much power the house is using when the house is asleep. So we can see the base load is in the order of between 500 and 800 watts. That's typical. It's a little bit high, but that's typical. My house is a lot more than that, and I can't explain why. Well, I can explain why, but I don't want to go there now. So typically, if you optimize your house, you can get the base load as low as 200 watts, 300 watts. That's a good idea to do that, to minimize that energy. All right, so what I mean with a typical load profile. Right, so typically, if that is how your house is using electricity, how do you use a solar system now to supply this or to bring savings. Look, obviously the effect or the reason for you wanting to install a solar system is twofold. You want to save money, the solar panels must save you money, and then secondly, obviously the battery must be there for backup during Eskom outages. Okay, so that is typically the load profile. So let's put some solar energy on top of this. Now the green graph, as you can see now, that is the sun coming up and the sun going down again, and that's on a nice sunny day. You'll see these little cuts out of the sun curve here. That is obviously cloud cover, and yes, it's quite significant. So a dark cloud takes up to about 90% of the efficiency of a solar panel. Can take the efficiency of a solar panel away just with a nice dark cloud. All right, so as you can see, early morning, all these red spikes and all the red energy before the sun is up, well, that's energy that you need to buy. It must come from somewhere else. It cannot come from the sun because the sun is not up yet. It could come from the battery, but then the battery must be big enough to store all that energy. So depending on what your objective is. So if you say off-grid, well, off-grid means that the battery must be able to cover all the red before and after the sun is up and down. All that energy must be stored in the battery. Then you're approaching, and we don't call that off-grid. We use our own term. We call that grid independent. But that's another discussion for another day. All right, so in this graph, we can see all the energy before all the red, before the green, that must come from the grid or somewhere else, not from the panels. And then while the sun is shining, all the green, all the red below the green, that is energy that is directly supplied from the solar panels. We call that, for obvious reasons, direct consumption. And that's where you want to be. That's the best place to be. If you could move all your loads to daytime, the dishwasher must come on later, the pool pump must run later, all that energy is used in daytime, that's direct consumption, and that's the best savings mechanism, is to use the energy directly from the sun. But then we can see there's quite a bit of extra energy. Look at all the green here. Where's all that energy going? We know that the clever people, it was Einstein or Newton or one of those, that told us that energy cannot be made or destroyed. So once we've harvested that energy from the sun, where is that energy going to go? It must go somewhere. So maybe it will go into the battery. So let's put on top of that now, we're going to get all the buttons sorted out, the profile of the battery. So if you follow this thin little line over here, this line indicates the battery state of charge. And the battery state of charge is indicated as percentage on the right hand side. So what does state of charge mean? It means how full the battery is. Like your cell phone, you see the little bars. The fuel tank in your car, you see the bars, how full it is, up to 80%. So here, this inverter was programmed, you can see, to maintain 80% state of charge. So how that basically works, if your inverter is smart enough to do that, you can program the minimum state of charge that the battery will maintain, that the grid will use then to keep the battery stable at that point. So when the battery discharges then to that set level, we call it self-consumption level of 80%, then at 80% it will stop using the battery, it will then start using the grid power, your Eskom power. When Eskom fails, then only will the battery drop below 80%, and when Eskom comes back on again, well then the grid will recharge your battery back to that preset state of charge level. All right, but the grid will never charge the battery higher than that percentage. Obviously you want the sun to do that. All right, so what are we talking about? We're saying that we've got excess energy. This green is excess energy. Maybe that energy went into the battery, was used to charge the battery. So as we can see, the battery here was at 80%, and there's a little dip over there. We'll see just now why there's a dip over there. But as the sun comes up, you see the battery state of charge increases. So obviously this excess energy over here, this extra green, that is used then to recharge the battery. And at some point the battery reaches 100%. As you can see, this is 100%, this line is 100%. So there, the battery reached 100% state of charge. Now the battery is full. Now still there's excess energy. Where's that excess energy going? The battery is full, the house is not using. The only place that energy can go, yes, you've guessed that, you can feed that energy back into the grid. And we'll see just now, we'll put the grid on top of that. And then for the rest of the day, we can see again, as the sun sets, the sun goes, obviously sets down towards to the west. The angle of the solar panels becomes bigger, the panels get less efficient, and now we've got big loads here, again a geyser and cooking, whatever, and surely, as we said earlier, let's look and see what happens. Let's look at the state of charge of the battery. Yes, so as remember the battery was programmed to 80% state of charge. So as the sun sets, there's not enough energy to supply this load. Now the battery is used. The battery state of charge drops. up to the point where the battery reaches the pre-configured self-consumption limit, as I mentioned earlier, and then at that point, the inverter makes the decision saying, I'm not going to let the battery discharge below 80%, I'm now going to start using the grid, and we'll see just now how that works. And then we start using the grid, the battery then later discharges further, and we'll see just now why did the battery discharge below 80%, and they need to recharge again to 80%. Now let's answer that mystery. Now we've added the grid. So the yellow is grid. So as you can see, during the small hours of the morning, the grid was supplying. Yellow was supplying, so the yellow is on top of the red, meaning the grid was supplying the load. And there's a small period over here where there's no yellow, that is only red, and you can see there the battery discharged. So obviously that was maybe an hour of load shedding. Something happened there was no grid supply available, and the battery was used. The minute the grid came back on, well, then the grid recharged the battery, and then the battery maintained 80%. So the battery didn't play any part from that when the battery reached 80% again. So all this energy early morning, that was bought from the grid. So you paid for that energy from your supplier. And as you can see, during the day, the minute there's excess energy, well, that excess energy is used to either charge the battery or it is used to supply the loads. And when the battery reaches 100%, you can see that there's excess energy, and this is below the zero line. So this is fortunate. It's one of my customers that lives in an estate where they can feed energy back into the grid. So here, the energy was fed back into the grid, and the customer gets compensated for that. His supplier actually pays him, give him some credits for that energy that he feeds back into the grid. All right, to follow the rest of the day, and I think you can do it yourself now. As you can see, there's a bit of use of the grid, and then here is no grid for that period. So that's obviously load shedding. So during this period, the battery carried the load. Remember the fuel tank? The battery was used to supply the load. Here, Eskom came back on again, and now you can see there's more consumption from Eskom than what the load is. Obviously, that excess that we're using from Eskom now is to recharge the battery to get the battery to 100%. Once the battery is at 100%, Eskom drops down, and then Eskom is just enough to actually maintain the load to keep the house the lights going. Does that make sense? Okay, so what did we say? We specified that we are looking for a hybrid system. We're on the mission now to design our own solution, our own hybrid system. We are budget conscious, so we need to make sure that the inverter is not too big, the battery is not too big, not too small either, and the same for the solar panels. And then to understand the relationship between the three, to know that, maybe to just summarize then from the graph that you looked at, is that all the energy that you saw on the graph before the sun is up and after the sun is down, if you want all that energy to come from your battery, well, then you need to calculate how much is that energy, and we'll teach you that in a subsequent video. How much is that energy, and what size must the battery be then in order to be able to carry all that load? And then tied into that, if that is the capacity of the battery, well, then you want to charge that battery with the solar panels. So then your PV generator needs to be big enough that it can actually harvest enough energy from the sun to keep the house going. Remember, the panels have to do two things. It must keep the house going, and at the same time, it must recharge the battery to get the battery full. So the relationship between the size of the battery and the amount of solar panels is really, really important. Often, and many installers make this mistake, the customer says, I want to save my Eskom bill is 3,000 Rand, I want to save 2,500 Rand. Then they just add a heck of a lot of solar panels on the roof. That is not going to work. As you saw in that graph that I just showed you, if you cannot sell energy back to your supplier, it doesn't help that you harvest so much energy during the day and you can't use it. So if your consumption during the day is little, is not much, yes, if you could move your geysers, put your geysers on clever machines or clever timers, and we'll teach you that with home automation, to get all these loads to run in daytime, that's direct consumption. Then you can have enough solar panels to supply all those loads. But then I would suggest is to install a monitor, get an accurate measurement of what does your consumption look like, that you can draw that load profile, as we looked at the graph. Draw that load profile, calculate how much energy you use during the day, how much before sun up and how much after sunset, that you know what size the battery and the panels must be. All right, it's been great. Thank you for watching. You know the dings and the bells and the whistles and the thumbs. Please do that. Follow us, and we'll keep on helping you to put your solar system together. See you.
We love the earth. It is our plan.